Inflammation is when your body's immune system activates a bunch of cells and proteins to get rid of things that could be a threat to your health, such as damaged cellular debris or bacteria. If you get a cut, inflammation will heal and remove damaged areas. If a person has a stroke, the injured part of the brain tissue causes local inflammation to remove and heal the damaged area. But it also triggers systemic inflammation throughout the body. And this systemic inflammation poses a major risk factor in other areas of the body and can kill you within days. So every year, 800,000 people in the United States experience a stroke. And mostly these patients end up in intensive care units. They can save you from the stroke, but when you're in the intensive care unit, the inflammatory response ends up causing a bunch of other problems that then kill you. Today, my guest is Eric Luthardt. He's an amazing inventor that I got to work on a brain surgery tool with at the Intellectual Ventures Lab years ago. He also had ideas for a kind of origami patch for aneurysms that we worked on. He's an amazing inventor. And these days, he's the inventor of a new way of solving this problem called R&R. What this does is stimulates the vagus nerve from what I call anti-inflammatory Airpods. It's an earbud you put in your ear that stimulates the vagus nerve, and it brings down the inflammation load so that you can survive after a stroke and the subsequent trip through the ICU instead of causing some other problem.
I've never met anyone like it.
He could hack anybody's phone in a matter of minutes. Who is that guy? Who can do that?
Carlos is the most interesting man in the world.
He's one of my favorite people on the planet. Inventor.
Wicked smart.
The master of cutting corners.
If you had a dead body in your trunk, who would you call?
He would get arrested immediately in a lineup.
I stood in line to get his autograph.
You know, his mouth can barely keep up to his brain.
I don't actually know what Pablos does.
A hacker magician.
Man of the future. Future.
I know we're both totally full of barbecue now, but
I may be
yeah.
10 points dumber having eaten like a pound of meat.
I was 10 points dumber trying to eat that much meat. You're a super unique guy who's had an amazing career, done a lot of invention, especially for someone in your field. And I don't even know, like, where'd you come from in the first place?
So I was born in Boston, but the early years of my life were in Germany. My father's a German citizen. My mother is Italian, but U.S. citizen. And I grew up there for the first few years of my life, and then my parents split up and I came to Cincinnati, actually, which I would say is more my formative years until college. The funny thing is people ask me like where I came from and what I did and how did I get here. What's actually I think really funny is that for the majority of my youth, people thought I was a slow learner. It wasn't really until kind of the end of high school where I had demonstrated at least some modest aptitude and got into college. That's always carried with me in the sense that I take a very humble tack in terms of my own personal sense of self, and that in some senses for ideas or visions or concepts, you got to work for it. For me, some changing points in my life were in high school, I ended up working in a neurosurgery laboratory. That was kind of transformative because there was this guy who just really believed in me at the time. His name was Keith Crutcher. Here's this kid who was thought to be a slow learner for a good portion of his life, and then suddenly somebody tells him they're smart. I was starting to learn about like how magnetic fields affect neuron growth and all this stuff.
And you knew stuff nobody else around you did.
Right, yeah.
Right? And so you start to sound smart.
Yeah, absolutely. But this guy took the time, and
Cool.
In retrospect, I have a big lab and I have lots of people and all things going on, and he had a big lab back then, and to think that this guy would sit down and talk to a 16-year-old for hours to kind of just talk about philosophy and science and theology and I mean everything. For me, it's a really important thing to pay that forward. He has, in my opinion, more capacity and potential than they give themselves credit for.
Yeah, right.
And I think we always have to be plumbing ourselves and others for what their potential is.
So did you find a way to do that? Have you drugged some 16-year-old kids in here? And
I do try to pay it forward. It's just some funny examples where there was a friend of mine, she was a nurse, and she had some 12-year-olds, and she was a parent, teacher, something, like she was overseeing like the classroom. And she said, I'd love to bring some of my students into kind of your laboratory to see what you do. Back then, this was 10, 12 years ago, we built the first brain-computer interface that was iPhone compatible.
okay.
And we created an app called, I can't even remember what it was called, like Brain Game or something like that. And something super simple where you make a little brain go up and down and fly over obstacles wearing an EEG headset.
Okay.
One of the girls used her brain to control things when she was 12. And apparently, I only learned this many years later, that apparently that transformed the girl's life. Like she now is in medical school and going into neuroscience and neurology, and that was the singular moment.
So cool. So was there one like that for you, or going into that lab?
You bet.
Did you get set on neuroscience then, or?
I guess the moment was, so the research that I was supposed to do was I was operating on chicken embryos, and I was removing the sympathetic ganglion from their spine. And these chicken embryos are about like 1 centimeter big, and you have to remove a portion of their spinal column to take out a nerve ganglion under the microscope. And so I was doing that, and another neurosurgeon in training, he was a chief resident, was doing the same thing next to me. And I could do it about as well as he could. And he's like, you're not bad at that. And so he took me into the operating room, and I watched a really famous neurosurgeon at the time, his name was John Tu, take out some brain tumors. And he would take me around, he'd take me to the OR, and I'd see these things. And that for me was a very transformative moment.
Just couldn't afford grad students, so
Well, actually, that's a funny story too. There was a program for taking high school students.
Oh, okay.
Part of the reason I got in is my mom got so sick of me always getting in detention. Like she wanted me to have something to do. And so I was always getting in trouble. So anyway, got sick of picking me up from detention after school. And so it got me involved in this program. And then that was how it all happened.
There's I think a lot of kids get misdiagnosed as slow learner. And the fact is they're just too fast of a learner. They're not being challenged, and they just tune out.
100%.
And that's part of what's happening.
I think there's huge variation, like learning style and engagement.
Right.
And I think also just emotional valence, meaning that a lot of kids, they need attention, or they need to be emotionally connected with. And,
that's right.
And I think one of the things that we lose is everything's measurable and quantitative. And when it comes to kind of learning in that early stage of life, so much of it is just about relationships. Like that, like having people who connect with you and believe in you and think you are more than what you yourself think you are, especially in the teen years.
Totally.
That is transformative.
Yep, it was for me. You would know more than me, but what my view is that brains are optimized for learning things they're interested in.
Yes.
And if you're interested in something, you can learn like crazy.
Mm-hmm.
And if you're not, then it's just pulling teeth. And nothing about what I just said maps to schools, as we know, right? And so it's very obvious what to do. Mm-hmm. Make it interesting. And then we know this, now we know this because of like fMRI, but we know this because of video games. Video games are optimized learning environments. Nobody's paying you to play a video game. Kids do it for hours on end with no outside incentive. They'll abandon school, work, everything else, food even, whatever, just to play a video game. And it's because the video game is constantly assessing you, and then it's putting a challenge right in front of you. Mm-hmm. And if that challenge is too hard, you get bored and quit. If it's too easy, you get bored and quit. It has to be just right. And so video games are outperforming schools. Now it's teaching you constantly. It has to teach you all the rules. You're not going to read a manual to play a video game. You have to learn everything in context. So it can teach you all that stuff. It's not teaching kids anything we give a shit about, but it's winning. And so I think we have to learn from that.
It does in fast scale the tension of purpose, right? Like the tension of achievement and giving you reward for achievement at a microdosed level.
Right. But here's the thing. If you had a 1-to-1 student-teacher ratio, then what a teacher would do is put a challenge right in front of you. They would know you, they'd know what you're interested in. It's time to learn pi, we're gonna learn it in the context of skateboarding, or we're gonna learn it in the context of electric guitar, whatever you're into. And that's what a good teacher would do. You don't even have to be a good teacher. If you only have one student, it's just naturally what you would do. And it's one of these things that kind of gets me wound up, because when people start freaking out about robots taking their jobs, I'm like, good, give your job to a robot, and then go teach one kid. If you say you care so much about education, let's see you put your mouth where your money is. Like, go do it. And because then you could move the needle. Then you really could have that experience for more kids.
Actually, the interesting thing is, maybe the positive side as we think about AI taking over lots of jobs, is that does that give us the latitude to return to really important relationships?
I think the answer is that we're already there. Like, we already all have plenty of free time. Our jobs aren't actually that hard. We're like sitting in front of a laptop. We're not like digging coal out of the ground. And so it's not like you couldn't come home from work and still have some capacity. We're squandering a lot of that capacity on entertainment, So I think our values are just poorly articulated and poorly adhered to. If we actually care more about education than entertainment, then all you got to do is grab a kid, sit down, start talking to them about pie and skateboarding, and you can get there. And kind of hoping that there'll be some inflection point here where people get so much free time that they just run out of Netflix. They've seen everything 12 times. It's like, okay, there's no entertainment left. I guess I'll go fucking hang out with a kid and try and teach him something.
Yeah, I mean, socialization is so fundamental.
Yeah.
I think another interesting thing, like when we think about technology today and gaming, are a lot of things where everything's on short time scales.
That's true.
And that, I think, is a challenge because I'm going to wax into a little bit of Eric Luthardt guesses, if you will. But one thing, if you look at, again, just the information age and how we're inundated, and basically whether it's video games, but tweets or just news, that we have so much information that we are always reacting to, I think fundamentally our attention span is diminished.
Yeah.
If you just look
that's
at
true.
collectively across the population,
It's
that
fair.
we have to react to so many things, we can't attend to things for longer periods of time. And I think it actually has an interesting kind of social consequence, is that if you are really exercising your attention, where you can read a long blog or read a book or do things, that you can start to process complex ideas and principles.
Yeah.
And I think what's interesting in this era is that I would argue that collective shortened attention span for how people are reacting, I think is one of the things that contributes to polarization of thinking.
Yep.
Because everything now has to be reduced into kind of simple sound bites
Yep.
or simpler digestible concepts. And nuance is poorly tolerated these days, or a complex concept is harder and harder to get across. And so I think it's an interesting time.
There's probably like the nuanced part of your brain, and then there's a different part of your brain that's called the sports ball part of your brain, and we're using that one, or even sports ball spectator. That's probably the third part for actually playing sports ball. Right. There's a spectator part of the brain.
It's like the reactive system.
That is just going full tilt. And yeah, I don't think anyone wants to argue with you about that point right now. That sounds pretty sound. But there's an open question of like, could you use the machinery of short attention span to teach people long attention span?
Cognitive activities generally, it's different than an athletic activity or a physical thing. And that's why one of the things I like to say is like your mind is a muscle, meaning that there is no reason that we can't start to have programs or exercise processes, just as we can train somebody to be a long distance runner. They don't start off being a long distance runner. When I remember I first started trying to just run for health, like getting a mile was not feasible. It wasn't happening. But again, you build up and slowly you build up that physical endurance. And similarly, I think that we can build up cognitive endurance, right? Yeah. And I think a lot of us are flabby with regard to our attention. And that just as we think about recess for the purpose of making sure kids are healthy, we need to have prolonged attention engaging activities to make sure we have longer attention spans to pay attention to important information and complexity.
I read this book when I was a kid called How Never to Be Tired. And the book is from like the 40s or something, ancient old book. And it makes the claim that your muscles get tired when you use them, but the brain doesn't. Now, you might feel tired because you've been doing a lot of things and maybe your body's not giving the brain what it needs, but the brain itself doesn't get tired, which is probably not true. And you could probably tell me how it's not true. But reading that when I was young and believing it, I think helped me a lot. My brain doesn't feel like it gets tired. I can feel tired and I can lose focus and I can get bored and all that kind of stuff. But at any given moment, if you put something interesting in front of me, my brain's ready to go. What do you think about that?
I think that the brain is a biologic system that demands energy. And importantly, one thing that we're realizing, demands sleep. The brain over time does accrue a whole number of metabolites that it has to clear through sleep over time. And if we don't pay attention to that, that results in, actually poor sleep is a contributor, for instance, to Alzheimer's, right? Like over time it is toxic. Now that said, I think that the brain has an extraordinary capacity to rise to the occasion when motivated. Meaning that, and again, some of it's biologic and some of it's scientific, but I think there's actually some extraordinary aspects of the ethereal aspect of our minds that we can rouse and mount our neurologic system to extraordinary capacities when demanded upon.
Yeah, it makes sense, and it's easy to imagine how that makes sense in some evolutionary context. But what?
I actually have a great example of this, like that I would want to highlight. It's really tangible in a certain sort of way. One of the first technologies that I developed is it's a brain-computer interface for stroke. We call it the IPSI hand. And when people ask me casually, like, what does that thing do? And I say, well, you use your mind to heal your brain. And so when somebody has a stroke, one part of their brain dies, but their intention to move is still there. As it turns out, that's located in a different part of the brain. But when you empower people's minds, their thoughts, to control a paralyzed hand with a robotic exoskeleton, their mind, by continually doing that, actually leads to the brain itself rewiring, and they recover function. But it kind of highlights, in my opinion, how the mind and our willfulness to do things with our thoughts can actually transform the architecture of our brain itself.
Yeah.
And that, again, in the setting of a stroke, it's an extreme example.
Sure.
But that applies everywhere. And again, our willfulness and our thought and our capacity to think has a direct impact on our brain's plasticity and malleability.
Yeah, maybe my belief that my brain could go without getting tired exercised it in that way.
You bet. Yeah.
It's so interesting. I'm tempted to run off track here, but when you go back to that metabolites that you described, that sleep is clearing out. I got a few friends who are super annoying because they only sleep 4 hours. The people who only sleep 4 hours, they're very productive. They're extra annoying for sure. I don't know. They're highly correlated with being annoying. But I'm always jealous that they only need 4 hours. It's like an extra life to live. Do you think that that's some kind of high metabolism that they have in their ability to process this stuff at night, or what's happening?
There is variation and if you look at how much people need to sleep, there is a bell curve, right?
Yeah.
And some people are on the low side and some people are on the high side of how much sleep they need.
Yeah.
You know, again, I'm speculating a little bit, but for those people who have less sleep, some people just try to get less sleep and it's ultimately not healthy. But for people who naturally have lower sleep burdens, they may just be better at metabolizing the daily accrual of toxins that allows them to have longer durations of wakefulness.
When you use the word toxins, what does it actually mean?
The number of different metabolites that your brain produces when it's metabolically active.
Okay.
One of the most well-known ones is beta amyloid. So increased neural activity leads to the creation of beta amyloid. And it's basically a beta-pleated sheet or a structured protein.
So it's a protein that's coming into bloodstream. Your brain
Not
is
the
using
bloodstream.
it. Okay.
So basically your brain produces it.
Oh, your brain produces
Like neurons produce it. Like the
it.
way
So
that
the brain gets stuff from the bloodstream, makes this protein.
Yep.
And then
Actually, I'll even correct you a little
Okay.
bit more. So basically, the brain has a complex metabolic process where it's creating action potentials, electrical signals.
Yeah.
It's creating neurotransmitters. It's sending out neurotransmitters. It's receiving neurotransmitters. That whole biologic process leads to the creation of beta amyloid.
Yeah.
It's a metabolic byproduct.
Yeah.
In the simplest way to think about it, it's neuron poop. It is like neuron feces that basically your brain needs to flush out with your CSF.
Got it.
But as we get older, or if we get less sleep, or there's a whole host of reasons that basically we don't do as good of a job of basically getting rid of the neuron poop. It aggregates, it becomes stickier, it clumps, and then those clumps of beta amyloid can lead to other types of proteins aggregating called tau. And then that leads to kind of destruction of your brain and Alzheimer's.
Wow.
But it's a biologic process.
Okay, I have a couple things I want to run by you.
Okay.
I know we should talk about inventions, but
I can talk about whatever.
Okay. All right. First one. I had a buddy who was one of the smartest people I ever knew. He was a trial lawyer. And it's terrifying. If there was a world record in the Guinness Book for trial lawyer, he would have won. When I knew him, he'd been a trial lawyer for like 20 years. He only has one client, which was the only remaining company in the world that put asbestos and insulation back in the 60s or something.
Oh my God.
And there were 1,000 companies that did it. They all got sued into oblivion. This one defended themselves. And because they were getting sued by everybody, they only did some of the insulation, not all of it. And so they defended themselves. And they have 100 lawyers. Every time they would fuck up a case and be about to lose, this guy, my buddy, his name was Steve. Steve would fly in, save the day. Never lost a case. And when I knew him, it was like 20 years into this career. He was also like one of the most voracious consumers of knowledge I ever met. Every day, a pile of books, movies, video games, magazines, would show up from Amazon every day. And he just was constantly consuming all of it at the same time. Always speaking 2 or 3 or 4 languages at once, learning a musical instrument, all at the same time. Has a stroke. And I went to see him and, couldn't speak, couldn't understand speech, couldn't read, couldn't write. And he started trying to fix this. He started by trying to understand speech. So you'd say Eric, and then you'd try and say it back, Eric. And when he saw me, he's like, he knew me, he had all the memories of me, but he couldn't say my name. He had to ask me my name. I had to tell him my name. He had to try and say it back. And then he had to try and map that name to the memories and everything else he knew about me. And he was able to do that over time. So a couple months in, he was able to do some of that and start having more like conversations. So he had to learn speech, learn to understand speech. Anybody else, I would have given up. This guy was good at learning, so he took it on. So then 3, 4, 5, 6 months in, he's getting better at that stuff. He takes on reading, learned to read again, very excruciating, learned from the ground up how to read again. And then the last one was learning to write. He's like, oh, well, I'm learning to write. I might as well come up with a font that I like. So he designs the letters of the alphabet. Because the first time, you and I, we just learned to write. Just whatever comes out is what you get. That's your handwriting. Well, he designed a style of letters, and then he practiced them and practiced them. And I go over to his house, and he's like, hey, check this out. I can write again. I'm like, okay, cool, awesome, amazing. I never thought you were going to get there, but cool. Right. But then he goes like this, check this out. And he puts the pen in his left hand, and he can write left-handed. It looks identical. It's like, check this out. He can write upside down. He can write upside down and backwards. You hold up to a mirror to read it. He didn't have to practice any of that.
Right.
He just got that for free. And this was like a super right-handed guy. Left hand used to be useless. Now he can write with either hand or whatever. And at the same time, as he was going through this, my daughter was like, I want to say 2 or something, 2 or 3, and she's stellar at speech, really verbal, conversational. And then all of a sudden she starts stuttering. Never stuttered before. She was speaking fine, and then all of a sudden she starts stuttering. And I'm like, she'd just get like stuck on a word. And I'm like, and that's what Steve was doing with the speech after the stroke. And he was going, he's Pablo's trying to get, and I thought, oh man, it's almost like there's different parts of the brain competing for control of the mouth. And your brain is like trying out different parts of the brain that are going to control the mouth. And everybody, one of them wins. And usually it's the same part of the brain. And we all can speak fine, and that's why we all have sort of similar brain mappings, you could say. But after a stroke, a quarter of Steve's brain is black in the MRI. It's gone. So obviously the part that was speaking before is gone. So now, like the drawing part of the brain took over for speech and took over for handwriting and this kind of stuff. And I realized with my daughter, who in a matter of months grew out of this, the thing, she was at a developmental stage where her brain was like, well, okay, you got speech, but maybe there's a better part of the brain that could do speech. And they're like trying it out. And then one loses and one wins, and you just go for their stuff. I made all this shit up as far as like my theory of brain development. But something like that I think might be happening.
Well, this notion of neuronal competition is a very real thing.
Yeah.
Again, I'd say the most famous demonstration of that actually came out of Washington University.
That's a real thing.
Yeah, it's a real thing. There's a guy, Thomas Woolsey, decades ago. Actually, ironically, I took over his lab space. And the famous experiment, and this really became a model for cortical plasticity, how the brain changes, is, again, the whisker barrel experiment. What I mean by that is, so when a mouse has whiskers, right? And each whisker, as it turns out for a mouse, has a cortical representation.
Sure.
So basically, they're very important to mouse survival and sensation of their environment. Now, if you cut one of those whiskers, what will happen is that whisker barrel or that column of cortex that's responsible for that whisker literally gets taken over by the neighbors.
Okay, repurposed.
Repurposed.
Yeah.
But I think that basic cortex is always competing for kind of functional utilization. And so it's like
that whisker was providing a signal, so therefore it was allocated brain resources.
That's right.
Once it stops providing the signal, those resources get
distributed. And so that notion that parts of the brain compete, that's actually a very real thing.
Okay, interesting.
And so another kind of way to think about that, now I talked about on the neuronal level with the whisker barrel, but Another way that we look at this is, and I think this is really interesting actually, is if you look at brain networks writ large in the brain, there's these fundamental canonical structures in the brain that organize certain types of cognitive functions. And actually, the way we look at it with what's called resting state fMRI, where you look at the networked organizational structure, and you can put them into hierarchical clusters. But if you look at the simplest clustering of brain function, there's the intrinsic network and the extrinsic network.
Okay.
So what do I mean by that? So the intrinsic network, and we have names for these networks like the default mode network, it is the network that processes your inner world, your inner voice, memory, rumination, reminiscence.
Okay.
And that network is quite literally anti-correlated and competitive with your extrinsic network. And the extrinsic network is your vision network, your motor network, your attention network, the parts of your brain that are involved with engaging the outside world.
Okay.
And so that's why, for instance, when people become depressed, quite literally the intrinsic network, like the default mode network, becomes dominant and more representative. The outside world facing network actually becomes diminished. And so when you see a depressed person, that they become inwardly focused, they don't talk, they ruminate, they perseverate around the same ideas, they're always fixated, and they're in these kind of continuous loops. And how do you break depression? In the simplest way, if you're feeling a funk, like not medical depression, you go for a run.
Go
you
outside.
go for a walk. You get exposed to sunlight. You watch TV. You talk to people. And the thing is, one of the most mood-enhancing things is when you are so engaged in something external to you that you forget about yourself.
Right.
It's actually a very interesting thing. And but competition in the brain is a very real thing. When it becomes medically unhealthy is when that competition becomes one-sided. In the setting of a stroke, like that whole competition is out of whack. In depression, that network is totally out of whack. And so finding like cortical balance, if you will, is really important for health.
Wow. Okay. On R&R, you figured out that there's this one big superhighway nerve running through the body that affects a lot of things. And so I don't want to lead the witness here. Can you explain what is the vagus nerve? How does this whole thing add up and what's going on?
Okay. Let me take a big picture view of this. So there's some fundamental components to our nervous system, right? We just talked about the brain. There's the central nervous system and there's a peripheral nervous system, right? That's like our brain, our spinal cord, and our peripheral nerves. And that's how we both receive input from the world and we produce output from the world. Then there's your autonomic nervous system. That's really the part of your nervous system that's separate, that really modulates homeostasis in the brain and in the body.
Runs on autopilot.
It's kind of like the person in the background just managing all the processes, right? It's your nervous system, and so there's two parts to the autonomic nervous system. There's your parasympathetic nervous system. We refer to that as the rest and digest system.
Okay.
That's the part of the nervous system that's responsible for consolidating, growing, resting, relaxing. And then there's your sympathetic nervous system. That's your fight or flight system. That's the part of your nervous system that basically reacts to the lion coming after you in the Serengeti. And these are deeply fundamental portions of our nervous system before we probably had higher order cognitive function.
Right, okay.
So extremely primitive and extremely important.
The
parasympathetic nervous system, your rest or digest system, that is governed by the vagus nerve. Spaghetti-like string nerve that comes off your brainstem, goes down your neck, and then basically it's different on the right and left side. On the left side, it innervates predominantly your organs. On the right side, it predominantly innervates your heart. And as it turns out, that system is really responsible for, again, things like controlling digestion and, importantly, controlling inflammation.
Okay.
So basically, again, putting it through this lens of fight or flight and rest and digest, when there's a big fearful thing that you got to react to fast and fight, your adrenaline goes up, your heart rate goes up, your inflammation goes up because that prepares you for an injury. Right? To react to something, to fight something, to run away from something. When you don't have that stress, but rather you are in a safe place, you are now ready to consolidate and grow and build your body, it's time to digest, it's time to reduce inflammation.
Right.
And that's what the vagus nerve is doing. It's controlling those organs that are basically priming it to be in a healthy, growing place, not react to a transient threat. And it was really learned over the past 10 to 15 years that of this relationship between the vagus nerve and inflammation. And it's also worth mentioning, like, what do you mean by inflammation, right? So in healthy conditions, you can think of it as your remodeling system, right? So basically, inflammation is this active process where your white blood cells, your body, is basically going to repair things. Let's say that you've cut yourself, right?
Yep.
You need inflammation to heal, right? So basically, it's got to clean out the dead tissue, and so that new tissue can grow and knit back together.
Okay.
Now, but very often, inflammation can get totally out of whack, and your cleanup crew becomes your wrecking ball. And high levels of inflammation can really be destructive. It can be destructive to really everything. It leads you to breaking down your body, leading to higher level. We talked about stroke, can increase your risk for stroke, heart attack, obesity, diabetes, and fundamentally, elevated levels of inflammation contribute to aging.
Yeah.
And so inflammation, when excessive and not properly dialed, is bad for you.
Is there anybody or any situation where people don't get enough?
Absolutely.
Oh, what does that look like?
100%. So basically, if people are immunosuppressed, they can't heal their wounds, their skin becomes thinned, then it is also very dangerous. So as an example, inflammation is important, for instance, when you're trying to fight cancer, because your immune system needs to mount a response to identify bad cells. Again, the cleanup crew, kill them and get rid of them. But if you're immunosuppressed, and some cancers immunosuppressed, lack of inflammation is an escape mechanism for cancer. So you want to get it just right, like getting into this Goldilocks zone. And so as it relates to R&R,
What's a good measure? Like, what do you measure to recognize what the inflammation level is or something?
there's different ways to do it, but like classically, like a lot of inflammation can be measured in the form of blood tests. The simplest one is called a sedimentation rate.
All right.
So the more inflamed you are, basically, the slower your blood settles in a fluid column.
Oh,
That's a very simple way to measure it.
okay.
It's called sed rate.
Is that because of the cell counts or what's the...
Cell count, antibodies, and cytokines make the cells more sticky. So basically, it just becomes more syrupy, for lack of a better way of saying it. And there's proxy ways to do it too. Yeah.
But going back to R&R, I guess the goal here is to figure out if you can affect the inflammation.
That's right.
Okay.
So maybe to take a step back again,
Yeah.
is that when we think about inflammation, where it plays an outsized role, is the intensive care unit. So the ICU is an extraordinary place in the sense that, number one, when you just look at it on the macroscopic scale, it's around a $254 billion cost to the United States. And even though only 10% of patients in the hospital are in the intensive care unit, they use 50% of resources. Wow. So it's very resource intensive, it's very costly to the global society. And one of the prime drivers, when you think about cost and outcomes and all this stuff that goes into it, is inflammation. And now many things can bring you into the intensive care unit. Maybe you've had a big surgery, you've had a stroke, you've had a bleed in your brain, you've got pneumonia, you've got COVID. And when you have elevated levels of inflammation, it's the body's pathologic response to that insult.
Okay.
And that repair crew, which has now become a wrecking crew, is leading to all sorts of bad things happening to you. Basically, muscle loss, diabetes, elevated blood sugars, hospital-acquired infections. You're just frail, you're sicker, you die more frequently, you're in the hospital for longer periods of time. And so getting your arms around inflammation can fundamentally transform the arc of care in the intensive care unit.
Okay. So do we normally just put people on ibuprofen a lot, or why doesn't that do the job?
Yeah, again, it's getting that right balance of inflammation, right? So if you totally immunosuppress people and like totally knock it all out, then they're going to have trouble fighting infections and they're going to have trouble healing their surgeries or their incisions. But if it's too high, then they have really diffuse damage. And so it's getting it just right. And so that's where, again, with R&R, we are figuring out a way to basically use your body's own nervous system to strike that right balance. So you have healthy amounts of inflammation and not pathologic and destructive amounts of inflammation. So for instance, and again, the way that we do it, as you know, is we do it in a non-invasive way. Now the vagus nerve, people have put implantable vagal nerve stimulators to treat disorders associated with excessive inflammation, like rheumatoid arthritis or inflammatory bowel disease.
Okay.
And
How's that going?
It's been shown to be very successful.
Wow.
And there's just some recent randomized trials that were actually positive. So the mechanism is very clear. Now, but you can't put an implantable device in a very sick person in the intensive care unit.
Sure.
And so what we're doing is that, as it turns out, and this is an accident of embryology, is that the vagus nerve has one cutaneous branch, like one branch that goes to the skin, and that's in your ear. And so the thinking is, if we stimulate that one branch in the ear, can we achieve the same effect as if we were directly touching the nerve in your neck through surgery? And so that's what we tested out. We've actually done now a couple randomized controlled trials in patients who have high inflammation and who are extremely sick.
Okay.
One is when you have a ruptured aneurysm.
Yeah.
Basically, you've got a bad bleed around your brain,
Yeah.
and these are some of the sickest people in the hospital. The inflammation causes their arteries to contract down and they get bad strokes. 50% of these patients die. They're really, really sick. And so basically the way we treat them is 20 minutes of stimulation twice a day, and that radically reduced a vasospasm, reduced their length of stay in the hospital, reduced hospital-acquired infections, and reduced cost of their care. And similarly, we did something for now ischemic stroke. So not that you've had a bleed, but basically, again, like your friend, a portion of their brain died, and we basically stimulated them for a few days while they're in the hospital. And once again, we showed we could lower those inflammatory cytokines, and basically the degree to which we could lower those inflammatory cytokines translated to better neurologic outcomes when they were being discharged from the hospital.
So they put that in layman's terms.
Yeah, maybe in layman's terms, what are some key differences? So let's think about those ruptured aneurysms. Under standard of care, a third of those patients went to a skilled nursing facility, meaning they went to a permanent nursing home or were permanently broken. When we treated them, none of them went to a skilled nursing facility.
Oh, wow, that's a big difference.
So in the stroke example, those differences that we see, and we measure what's called NIH stroke scale, those differences that we see that were differential between the changes levels in inflammation, that could mean the difference between whether you go home or whether you've got a permanent disability.
Yeah. I remember you telling me that a lot of people come into the ICU with a stroke. You guys can do surgery, save them, maybe with some damage, but they're not dead. And even while they're still in the ICU trying to recover, they'll have another stroke.
That's absolutely right.
Because of the inflammation.
That's exactly right.
Okay.
And so we refer to that as like waiting to survive, right?
Yeah.
Like, so you've had the initial insult, and then your body's reaction to that initial insult can kill you.
Your body overreacts.
Exactly.
And so the hope, I guess, with ORNR is that we'll be able to intervene with the vagus nerve stimulation, reduce the inflammation, keep them from even having the second stroke.
That's right. That's just one example.
Yeah,
like,
just one. There's probably
there's a whole cascade.
Effects.
Like once your inflammation is elevated, you are so much more susceptible to all these costly and damaging complications, and we're going to try to reduce all of them. And again, I think the R&R device has this little blue winking light, and ultimately, I want to see every patient in the ICU have a little blue winking light in their ear.
Yeah. Can you make it not blink? Because the blinking is going to set off the Pokemon effect or people.
We'll come up with something.
Cause a seizure. Yeah. So that's pretty exciting. I can see why you're so fired up about it. Like,
absolutely.
And just since I know and the audience doesn't, why don't you describe the device and what the intervention
actually
really is?
You know what?
Oh yeah.
I can
show me because we're at your lab.
Yeah.
I've never seen one. This is exciting.
Yeah, we now have our kind of fully integrated device now, and
it
really looks like an earbud.
All right. Can I hold it?
Yeah.
Yeah. Okay. Can I put pictures online? Not yet.
yet.
Okay, no problem.
And these will be disposable, so it's easy to use for the staff. And basically, the nurse pulls out the tab.
Okay.
It's adjustable for everybody's ear.
Oh, that's interesting. I see.
And so put it in the ear.
Okay.
Dial it up.
Oh,
it's
cool.
not coming out.
Wow, smart, clever.
And so basically the nurse then presses a button, and then this is sped up for demo purposes, but it's 5, 10, 15, 20 minutes. And then basically once it's done stimulating, a little checkbox goes off. You're done with it. You take it out.
How long does it
throw it away.
typically stay in?
20 minutes.
20 minutes. And then how often do you have to do that?
Twice a day.
Twice a day. You may have just said that.
Yeah.
Okay, and then these are the electrodes.
Yep.
Huh. You described it as being very important to get to the exact right spot.
That's right. And this is actually totally designed to do that.
Oh, it is?
Yeah, so basically the way we made this earbud canal portion and the electrodes and the adjustability, we did, again, not to totally nerd out, we did finite element modeling. So like where it goes in the ear really is optimally positioned with the electric field and the way we structured these electrodes and the size of the electrodes, so that it really, it stimulates the nerve, importantly, without you even sensing it. So you don't feel anything.
Yeah, amazing. Wow, that's super exciting. I'm thrilled that it's happening. So what has to happen now? You have to go do more trials.
So ultimately, we're in the phase now, we've got our fully created device. Now we're designing for manufacture.
Okay.
We're getting ready to ultimately apply for a pivotal trial.
Yeah.
So that basically in subarachnoid hemorrhage, those patients who have ruptured aneurysms who are extremely sick, that's our beachhead population. Basically, we'll do a randomized trial to prove we can reduce these toxic complications like vasospasm.
Okay.
And so right now we're in the process of raising capital to prepare for that pivotal trial.
Yeah, and then is design for manufacturing a challenge, or you got the help you need for that?
Yeah,
Okay.
we're all set. I
Okay.
think the next year or so of kind of design for manufacturing, verification, validation, these are not risky things. You just got to stack the bricks to get ready.
Yep, got it. Wow, I can't wait. Anything we missed on that?
No, again, I think that fundamentally, imagine, again, like a simple wearable device
It's just-
that can like have pharmacological
No
levels
wires
of-
sticking out, no battery pack. It's just great.
Yeah, essentially think of it as a safe digital drug with no side effects that
Yeah.
can really be transformative for care.
Wow. And you only need one in the left ear.
One in the left ear.
Pretty awesome. I have one other topic I want to run by you.
Okay.
We can cut this out if it doesn't go well.
Sounds good.
Presumably someone has told you to, but you haven't yet listened to the telepathy tapes.
I don't think I know what the telepathy
You don't know what it
tapes
is? Okay. I'll describe.
are. Okay.
It's a podcast. I think there's 8 or 10 episodes. In each episode, they go visit a nonverbal autistic kid.
Uh-huh.
They put the kid in one room. They put the kid's mother in another room. They put a random number generator in front of the mom. And the kid can tell you what she's seeing. Not sometimes, all the fucking time. 3, 4, 5, 6, 7-digit numbers. Nobody can explain it. Some of these kids can, it's not just random numbers, they can literally tell you what the mom is seeing. Can read the mom's mind. The contention is they can read the mom's mind. It's not always the mom, sometimes it's another caretaker. Some of them can do it with multiple people, some of them can do it with everybody. It's totally unbelievable and obviously complete bullshit. So these are kids who don't speak, but they've learned to communicate with an iPad so they can type things out. And so they're able to communicate what they're seeing. And they go to Mexico and India and all over the world to meet these kids. There's a bunch of them. But the contention is not just that some of these kids can do it, but that all of them can do it. And it sounds like witchcraft, I know. But suspend disbelief for a moment.
Okay.
Who knows what's going on? There's a lot of argument. The whole internet is fired up because this became a very popular show. Everybody listened to it. Everybody has an opinion about it. Anybody who's into science thinks it's bullshit. Everybody who has an autistic kid thinks it's totally true, and finally we have the answers. But never mind that. If you just take for a moment the possibility that there's some channel of communication, there's some channel that allows a thought to be read from outside the brain. And we don't know what that is. There's a long history in science of detecting new phenomena that we never thought possible before and couldn't explain. And so it's entirely plausible that something, we know that like quantum entanglement exists. That's probably, with what we know now, the most obvious explanation is
Yeah, that's where I'd go.
that's where I'd go to, but and we don't know enough about quantum entanglement to like
Right.
explain how it could be communicating an actual thought, but
Right.
whatever. If there's some channel, what happens with these tests is that the people who perform the tests are completely convinced. Everybody who watches or listens to the tests thinks that whoever performed them must have fucked up. So, so there's going to be a window in time here where we're going to go, replication will get done, and we'll figure out if they did a poor job of the tests or something else is happening. All the people who did them claim they tried to control for reflections and sound and all the other ways that somebody could cheat. But anyway, if there's some channel, we should be trying to find it. And so I just figure, okay, maybe there's a channel. Because it's taboo to even consider this possibility, nobody's researching this stuff because it would be professional suicide to admit that you're working on this stuff. But
Although I have a funny vignette on this.
okay, we'll get to that in one second. But here's where I'm going.
Yeah.
If that channel exists, and we can find it, then something very interesting happens, which is that becomes your brain-computer interface. And now, the least potent people in the world, who are nonverbal autistic kids, overnight become the most potent people in the world because they're the only ones who can talk to the computer with their brain. We're all saddled with keyboards and microphones and fucking talking to the computer. These kids would have Wikipedia in their brain. They would have YouTube in their brain. They'd have ChatGPT in their brain. And so overnight, they would become the most capable people in the world if we can find that channel.
Well, it's interesting. I would say that neurodiversity is diverse for a reason.
Yeah.
In the sense that there's an evolutionary reason why we have, different manifestations of intelligence and intellect and social capability and social interaction, because different situations may require alternate capabilities. I heard somebody once say that autism is nature's backup plan for humans. On the issue of, is there a channel, is there connections? I think, again, and maybe this goes back to me being a slow learner as a child, you always have to be humble about the fact that you may not know everything.
Yeah.
Right? I think if you would have asked somebody in the 1700s, an overcompetent, academic, I think many of the things that we do see and think are capable now would have been completely poo-pooed.
No question.
300 years ago as simply being inconceivable, right?
Absolutely.
And so you always have to take a humble notion to improbable possibilities. And that should excite curiosity and exploration, but concurrent rigor, for objectivity. And so when people say this stuff, maybe on the surface, like, I have to guard against my more elderly professorial inclinations, and always be open to kind of the fact that there could be novel ways that our nervous system interact. I mean, one thing, as I think about it, I'm really stretching my knowledge here, but for instance, certain animals have magnetic sense so that they know where true north is.
Yeah.
Right? Like,
exactly right.
That's a magnetic field that we don't have. And also there's studies that have been done when you have two people wearing an EEG, and it's been shown that basically when those people basically come to an agreement or come to an understanding, their brain rhythms actually start to kind of co-fluctuate together. So there's something, about that interaction that's letting their electrophysiology become more coherent. So are there things that, about how the nervous system can interact with another nervous system that may be beyond our current awareness? I certainly won't dismiss it, right?
Yeah.
Now, doesn't mean, but that still means you got to prove it to me, right?
Of course.
Like, you know what I mean?
No question.
But I think you just have to always maintain a healthy dose of curiosity.
Yeah.
And when it comes to these more controversial items.
Yeah, it's a wild one. I remember just a year or two ago reading about some research where they sort of figured out that a neuron can not only detect a signal, can detect the direction of the signal. And I don't know if that was actually new or just new to me, but at some point it was. And realizing that, like, oh my God, the amount of resolution we thought we needed to model a brain
absolutely
just went
insane.
Up by orders of magnitude.
Absolutely. Not just the number of neurons, the number of connections and distinct connections and the manner, the massive scale at which we are going to have to model that. There was just a recent, I think it was a Science or Nature paper, where they effectively just mapped the connections of 1 cubic millimeter of a mouse visual cortex was a major accomplishment, right? And that took a whole team years to accomplish. And you think about the human brain, it's really extraordinary.